So for this first problem, I'm going to look at section A, and I'll do problems 3 and 4, dealing with examples of finite quotient groups. I think this is a good collection of problems to do. I'll do some, and you'll do some at home. So that way we can really get some experience and some familiarity working with quotient groups. And so for this example, the group in question is D4, the symmetry group of the square. And I'm going to do two examples actually. I only wrote three here, but I'll do this one and also the next one with two subgroups, one of them being the group consisting of just E and R squared, and one of them being the rotation subgroup. There's a little bit of a typo in this problem. I mean, there are a lot of typos in this book, I've noticed. But this one in particular is a little bit weird because it has like just the powers like 2, 4, and 5 or something. But 5 would be the same thing as 1 in D4. And then where is the one that's specifically rotation of order 3? Or sorry, the power 3? I'm not sure. But the only reasonable interpretation for this question is that these are the two groups that we're supposed to look at. So the first thing is by Lagrange's theorem. Lagrange tells us that the order of a subgroup divides the order of a group, and in particular, it counts the cosets. So Lagrange applies in general, telling us how many cosets there are. But in the case that the subgroup is normal, the cosets are exactly the order of the quotient group. And so we get this very natural looking formula that the order of the quotient group is just the quotient of the orders respectively. And so D4 mod H1 should have order 8 divided by 2, or 4, and D4 mod this H2 will have order 8 divided by 4, which will be 2. Now, this allows us to immediately dispense with the second example because there's only one group of order 2. The group of order 2 is isomorphic abstractly to Z mod 2Z. And so to convince ourselves of this, we can just remember what the elements of this group are. We have the 4 rotations, and then we have the 4 reflections. And we have the rule SR equals R inverse S. So if I want to mod out on the left by H2, then what I'm saying is whatever the element that I want, any representative of an element looks something like SI R to the J in the list of elements, which is equal to R to the minus J SI using the rule. And so now if I want H, I want to know the coset of this thing. That is H R to the minus J S to the I. This gets absorbed into this and just gives me HSI. And I can either be 0 or 1, right? Because the reflection has the property that S squared is the identity. And so that's the Z mod 2Z. The quotient group that we're looking at here simply records, maybe we should write this down, D4 mod H2 records orientation. In other words, is there a reflection or not? If there's a reflection, we call that orientation reversing. And if not, we call it orientation preserving. Okay, so that one's pretty easy. Let's take a look at this group with H1 here with 2 elements. Let's rewrite it down below. And let's try to work out what are the cosets of this group. And we know we're looking for a group with 4 elements, and we know there are only 2 groups with 4 elements. There's Z mod 4Z, and there's the product of 2 Z mod 2Zs. And so it's an interesting question to ask which of these two groups we would get when I look at D4 mod H1. I shouldn't write equals, I guess, right? I guess I should write isomorphic too. But let's see if we can work out the multiplication table, and then we will know which one it is. So the first thing we have to do is come up with all of the elements. The elements are the cosets of H1. So let's try to find the cosets of H1. The first is there is, of course, H1E. That's always there. Let's try, and then we have H1R, also obviously present. And now we need to know, what about the other choices? Well, our other choices seem to be, we could try H1R cubed. What's this thing? Well, this is the collection of elements of the form things in H1 times R cubed. But what we see is that is the same thing as H1 R squared times R, or H1 R. So H1 R cubed is already here. So we got that taken care of. Then similarly, we have an H1S, and we have an H1SR, but not anything more than that. Because if I try to do an H1SR squared, then using the same kind of math as before, I get R to the minus 2S, and actually that's the same thing as R squared anyway. That's just H1S again. And with R cubed, the situation is the same as over here, except now with an extra step of intermediarily, is that even a word? I don't know. Moving the R cubed past the S. So here are our four cosets. We knew there would be four, we found four. So these are the elements of this group. And now we want to work out the multiplication table. So I'm going to stop writing the H1s for the purpose of making the table. We're still going to need them when we do the actual calculations, but we have E, R, S, and RS. And we know anything times, right? We know how to do this now, right? Each of these things that appears, first we put anything times E as itself. On the other hand, to fill out the rest of the table, we know some stuff, right? Like for example, let's use left to right notation so that the entry in, I don't know, this slot means R times S. Well, if I do that, then R times S is of course just RS, right? H1R, H1S is evidently H1RS. And then H1R and H1R, those make E because R squared is in H1. And that makes this one forced to be S because of the Sudoku property. I feel like it's been a very long time since we discussed the Sudoku property, but here it is at work for us. And actually, with this information out of the way, we're pretty much ready to finish. Let's just do one or two more lines and then we'll clean up. H1S, H1R is H1SR, which is H1 R inverse S, or R cubed S, or RS again. So you see, because by absorbing the R squared with the familiar logic, this becomes also RS. That makes this S as well. And now S times S is, of course, E. And that makes this R, and that makes this R, and that makes this E. And so we're done as far as computing the table goes. The question becomes, which group is this? And let's just have a little bit of an inspection of this table. What I'm noticing is every element on the diagonal is E. And so every element, let me write that down, on the diagonal is E. In particular, every element has order 2. And so of the two choices, here there's an element of order 4, right? This one is cyclic, whereas this one, every element is order 2. And Therefore, it's this one. And so what we see is that D4 mod H1 is isomorphic to the Klein 4 group, which we also called V in the past. But if you want to be specific, Z2 cross Z2. And we're done. Very cool.